Esto es Health Tech Dialogues, un puente desde la gestión y la política sanitarias hacia la transformación digital, los datos y la inteligencia artificial.
Today we are hosting Tom Fitzgerald, a molecular biologist and senior staff scientist and faculty at the European Bioinformatics Institute.
Tom, we're here today to talk about your fantastic and remarkable work on called Delphi 2M. First of all, I would like to ask so that everybody that's listening and that even when the paper was news all around the world, but for those who are not fully aware of what this means, could you specify a bit what problem is this model, this AI system solving in terms of risk prediction for disease?
Absolutely, and thanks for inviting me. It's really nice to talk about this work. It's actually a fantastically satisfying piece of work that we've done, probably over the last 18 months, from conception to actual publication in Nature, and it was really satisfying to us to see the amount of attention that the work has got worldwide. So it's been a fun period of time. But yeah, just to give you a sense of what it's all about. So we've been in the healthcare modeling disease risk estimation space for quite some time, and that would have been in the past normally using kind of more classical statistical methods or machine learning techniques like hidden Markov models and things like Cox regressions, for example. But it struck us, a while ago that really the later new kind of next generation of AI models really is well suited to this particular task. So what we've done with Delphi 2M is we've made some real innovations inside the architecture of generative transformer models. So the type of model that's used in ChatGPT, for example. And in particular, we've been able to use a different representation or innovation in terms of how you can represent time within the model. Okay, and what we're really lucky to have is access to these remarkable large human cohort datasets, such as the UK Biobank and other health registry datasets. And what Delphi 2M is really all about is using a generative transformer architecture to model all disease within a population at the same time and map to continuous time. And what that allows us to do is to uncover complex interactions between multiple factors all across continuous time, across somebody's life course, and results. It's remarkable to us to see that actually the predictive performance of the Delphi 2M model across a very broad set of disease classes. The current model includes over 1,200 diseases, all within the same space. And for a lot of those diseases, the predictive accuracy is similar, if not better, than single disease risk models. But you have the real benefit of having all disease mapped on the individual level and being able to estimate risk of disease for everybody in a population at any point in their life and any point into the future. And one of the key points, I think, is that we've been able to really highly calibrate our time estimate. And for many of those predictions remain accurate many years into the future, in some cases 10 to 20 years. So that's kind of in a nutshell what it's all about, and it's really a fantastic piece of work to be involved in. Very satisfying to see the result.
Let's go a bit technical.
Yeah.
Why transformers, GPTs, are a better or a good methodology for tackling this kind of problem compared to the traditional, if we can call them traditional, machine learning models?
Yeah, so I think my take on this is really being able to model all disease all at the same time within the same framework. With some classical machine learning methods, that's quite difficult, or at least it's difficult to interpret. And the natural way in which these types of models are trained, which is obviously, next token prediction, it kind of lends itself very nicely to that problem space where we're trying to predict what's most likely to happen next in somebody's healthcare trajectory. But the classical models, which use kind of sequence embedding or sequence encoding techniques, would very much be really only concerned with what's going to happen next or what's most likely to happen next. What Delphi 2N does slightly differently is that it also incorporates that time aspect. And in health modeling, that's really important. You don't only want to know what's most likely to happen next for somebody, you want to know when, and therefore that can inform, what an appropriate intervention step might be, for example, within a clinical setting. But it also allows the model to learn this kind of codependence between disease and timing, which is one of the factors of the model that we're very, very happy with.
Among all the findings, is there anything in particular that surprised you more, in both clinically or methodologically?
Well, it's a fantastic question. So I think overall we were surprised with how performant the model is, and across the time range. That was amazing to us, and it is partly to do with the innovations that we've made under the dataset. I think in terms of very specific diseases, there isn't really those which would be, well, we haven't dug into it in a huge amount of detail, but there's not a lot of the predictions make sense, both in terms of sex, age, characteristics, and other factors that go into elevating somebody's individual risk. And as you would know, it's quite difficult to interpret those factors, and one has to be quite careful about causality. So so I think really the main surprising thing and the very satisfying thing is the overall performance across a very broad set of disease classes, and that those predictions make a lot of sense given clinical or lifetime settings.
And so you mentioned causality as one of the main problems, which indeed it is. And in that regard, we know that there are groups around the world working on how to apply machine learning to causality, or the other way around. Mm-hmm. Maybe another one would be how models generalize, right? That's the way in which you apply them in real population. And actually, in this paper, we saw that when transported into the Danish population, the model performed a bit poorer compared to the UK. How you see this evolving into real life application?
Yeah, so that's actually one of the really satisfying parts of the paper, I think, in my view, is that we were able to train a model in the UK setting, transfer it into a totally different healthcare system, which in this case is Denmark, without any retraining or fine-tuning of the model, and just evaluate that model within the Danish setting. There is a marginal loss overall in terms of predictive accuracy, but actually it's very marginal. So it's still a very performant model, even in a totally different healthcare system. And what that shows you is that actually the model's capable of learning some general patterns within healthcare trajectories, which are transferable across at least 2 different healthcare systems. That's super nice to see. And a good illustration that the model has actually generated some meaningful insight within a healthcare setting. And it's worth saying that was a totally held out zero-shot validation test set in about 2 million Danish individuals from the Danish healthcare registry. So it's a significantly difficult task to train a model within a different healthcare setting and transfer it and have such good performance across a broad range of diseases in a different healthcare setting. So that was great. I think overall one thinks about this probably in terms of having the ultimate situation is to train a model within an individual healthcare system. So if we trained a Delphi 2M model in Denmark, one would expect it would be better in terms of overall predictiveness in the Danish population. And of course, if one is only thinking about or only really cares about predictive accuracy, then maybe that generalization is less important somehow. But of course, when one wants to really try to interpret some of the features underlying the predictions that models are able to make, then I think generalization and biases need to be kind of considered quite carefully.
And talking of different healthcare systems, normally we see how different systems, even in Europe, they collect data in different formats and ways. And one of the things is that we know that in many cases, maybe not so much with the Nordics, but generally speaking, there is a lot of rich information and value within the free text of medical records. Mm-hmm. How is this work considering unstructured information, and how much do you think it would benefit from natural language processing approach in order to enrich the data sets?
Yes. So I have quite strong views on this, I suppose. So actually I don't, so I think there's benefit to adding some natural processing methodologies on top of a Delphi model, for example, or incorporating some of that information. But I want to make very, very clear that the Delphi model is very different to a kind of clinical assistant or a language processing model. There could be some, like a module that one might think about to process free text from doctor's notes, for example. But my slight concern there would be some pollution of the data set using or the predictions using. I think it's an area that's worth exploring further. But I would like to mention that there are lots of other types of data modalities that are somehow potentially, in my mind anyway, even more interesting to incorporate into Delphi style models. And we are actively working in that space. So for example, genetic information, how you best represent genetic baseline risks for disease and how that interacts with somebody's healthcare journey is very exciting. It's something that we're working on. There's also information, for example, in biomarkers, laboratory tests and prescription records, which are more, in my mind at least, natural extensions to the Delphi model, where we would have, for example, a multimodal Delphi implementation. And all of those different data modalities add some benefits in certain areas. And if one's thinking about purely prediction, you know, the evidence that we have and the work that we're carrying out is that each of those data modalities can add particular value in particular settings. And so having a kind of more multimodal view on these types of models is a really fascinating space, I think, which
Indeed, it is. Multimodality is for sure the way. So talking of impacts on the healthcare system, one of the things that I thought when I read this was, wow, if now we have this tool, how, you know, ethically for a country, how mandatory it becomes to apply it. And if we do so, if they do so, for example, in the NHS, how expensive is it going to be to call the patients who are at risk of something and test them? What is the impact in terms of ethics, of health economics? What I'm trying to say is that I think this is very brave as a healthcare system to go real predictive and preventive, because everybody talks about it, but then it changes budgets, it changes the way in which you behave. And obviously it's the right way, it's the proper way to do things. But I'm wondering if healthcare managers and politicians will agree in the first place with this way of doing things. And how do you foresee the system changing with this evidence that you're putting on their tables?
Yeah, I think it's a really interesting question, which requires quite a lot of thought. The way I look at it is that these types of models provide a new tool that could be in the future very beneficial to healthcare providers and policymakers. There, of course, needs to be quite a lot of regulation and policy review before implementing such a tool within a kind of clinical or a more management setting. I think in terms of direct clinical use, so one could imagine having a kind of early detection system or a clinical assistant that helps doctors view individual patients in light of the factors in their life that are driving a model to predict that they are at risk of a certain condition at a certain time in their life. That's quite an easy way of thinking about how these models could be applied. I would say that that's 5 to 10 years down the line, once there's been sufficient regulation and policy reviewed and put in place to allow such a thing to happen. That's my expectation in terms of timeframes. But there's another very interesting part, which is more to do with management of healthcare resources and how those resources are likely to change across time. So what's the likely burden in a whole population or a subpopulation for different disease classes within the next year or 5 years? And that has an impact in terms of healthcare planning, resource planning, and cost, essentially. So that's a more tenable use of these models, I think, in the short term. But there's certainly risks to be considered, and I think that's really what I'm getting at with this need for regulation, testing, and evaluation. One area where I think you can learn quite a lot of or draw some comparisons to is the genomics space and the genomics medicine space, which has been operating quite well now for many years, for over a decade, and has encountered this problem of, for example, incidental findings or findings that people don't necessarily want to know, and the ethics behind that level of information on an individual basis. And I think, with the rise of our AI in healthcare, there's quite a lot of lessons that can be learned from how the genomics community, and in particular the genetic testing laboratories and the genetic medicine space, have applied successfully with many national genetic testing services up and running and making diagnosis on the individual level. So I think there's some lessons to be learned there. But certainly requires some careful thought.
Yes, I was reading this editorial letter like 1 year ago or so from Eric Topol that said something like, I think it was in the New York Times, and he said something like, we can already find out who will have Alzheimer within 20 years, and we shouldn't, right? Yes. Because we don't have a treatment. Yes,
exactly. Yeah. Exactly. I mean, that's a very good example. That's a good kind of thought experiment. But I think there are there's certain to be other conditions where people may or may not want to know, but I think that comes down to consent, really, potentially, but I think I think there's so much potential benefit to the individual and to the healthcare system as a whole that that these models will start to be used on the large scale in the future.
Are we going to a medicine where the model of I have symptoms and signs and I get a test and I get diagnosed with the right context and everything else? Of course, it's not entirely algorithmic, we know that, but are we going from that model to a model where we have sort of windows into the disease biographies of patients, and we we handle that like a continuum, longitudinal continuum of disease and health? Is the way, is medicine really going to a disruption, or this is just one more tool, but the center of the workflow of healthcare will be the same, but more informed?
Yeah, I mean, I would go with the latter there, really, that this is an advanced tool that has the potential to improve healthcare delivery and resource planning on the population level. There's another part to it, I think, which is more within the research setting, potentially, which is all about understanding factors and understanding disease in a more fine-grained way, and potentially understanding the impact of intervention on different subsets of individuals given their health history and other factors. So yeah, that's my take on it. I think there's clear benefit within clinical settings that needs some further regulation and testing and everything, but then the research part has a lot of potential, for understanding multiple factors about an individual, which could, for example, be genetics. It could be some other factors or family history, or where you can really use these models to understand what and also critically when within somebody's life those baseline risk factors really make a difference to their potential health journey.
I'm particularly interested, and you mentioned it in a way, in how we make models that work very well and perform very well, like this one, a reality for physicians. Because many times we have very nice scales, risk scales, tools, but they end up being unused. And obviously there are workflows where you can include them, but then there's a lot of friction there. We've played with some ideas in the past, like maybe we should start where there are already clinical situations taking place, like for example screening tests, and we can apply the AI systems there. Or maybe it's going to be our generative AI companions, our agents that are going to be using models like Delphi 2M. I don't know if that's too disruptive as an idea, but how do you see this being landed into actual humans that don't have time and energy to include new tools?
Yeah, so I think it's really interesting, and it will be variable between different healthcare systems, different organizations, how one might want to use such models. I mean, I think, as I mentioned, the most, at least in my mind, a very clear use case would be as a way of presenting the likely risks for an individual at a doctor's appointment in the context of all of their previous history. And that might be something that's actually quite easy to implement and useful to the clinician. But then the other part, which is more using these models to really inform healthcare planning and resource management, has lots and lots of potential for increased care on population level, and that activity, I think, is more on the organizational level. So yeah, predictive and also, frankly, also in the research space. So what is it that could be done to improve health within a particular setting?
Tom, it has been a true pleasure to be able to meet you and talk to you. Congratulations.
Thank you very much, and lovely to talk to you. Thank you for the invite.